오케이. 챕터 7 optical instruments라고 되었습니다. 그래서 우리 지난 챕터 1, 5, 6에서는 그냥 아주 기본적인 내용들, 우리가 이 수업에서 어떤 내용을 다룰 것인지에 대한 이제 소개를 하였고, 그 이후에는 이제 챕터 5, 6에서는 우리가 무엇을 측정하는지, 일단 챕터 5에서 시그널이라는 걸 우리가 측정할 것이며, 시그널을 더 잘 측정하기 위해서, 다시 말해서 이제 SN ratio, 시그널 투 노이즈 레이쇼를 증가시키기 위해서는 어떻게 해야 되는지, 노이즈를 어떻게 줄일 수가 있는지, 이런 점들을 다뤘었고, 지난 바로 직전 이제 챕터 6에서는 우리가 이 수업에서는 주로 분광학, 빛을 이용한 그런 분석 방법들을 다룰 것이기 때문에 그냥 빛의 그냥 기본적인 특성들, 이런 내용들을 다뤘었습니다. 그래서 뭐 그런 내용들은 다 이제 여러분들이 일반 물리나 일반화학에서 배웠을 만한 그런 내용들이기 때문에 그냥 대충 이런 것들이 있다 정도로 저희가 넘어가긴 했었는데요. 그래서 빛의 어떤 특성들, 웨이브로서, 파동으로서의 특성, 그리고 뭐 입자로의 특성들이 어떤 특성들을 가지고 있는지 그냥 간단하게 여러분들이 기억을 해 두시면은 그런 특성들을 활용을 해가지고 우리가 앞으로 이제 분광학, 어떻게 그런 빛의 특성들을 활용을 해가지고 우리가 분광학에서 이 빛의 특성을 활용을 하는지에 대해서 하나씩 다루게 될 겁니다. 그래서 먼저 챕터 7에서는 우리가 분광학을 다룬다고 했는데, 그럼 빛을 다룬다는 얘기고, 그러면 우리가 뭔가를 측정할 텐데, 빛이 뭔가 변한다든지, 이런 것들. 우리가 챕터 6에서 빛의 여러 가지 이제, 변화하는 특성들을 우리가 살펴봤었는데요. 예를 들자면은 뭐, 흑광, absorption, 뭐, 형광, fluorescence, 뭐, 인광, phosphorescence, 뭐, scattering, emission, 뭐, 이런 것들. 이런 것들을 우리가 실질적으로 측정을 함으로써, 예를 들면 어떤 샘플에 어떤 물질이 들어있는지, 얼마나 많이 들어있는지, 이런 것들을 알아낼 텐데요. 그런 걸 측정하려면 당연히 측정 장치, 측정 장비가 필요할 것이고, 그런 장치들이 어떻게 구성이 되어 있는지, 물론 장비들마다 다 다르겠지만, 기본적으로 옵티컬 인스트루먼트가 어떤 것들로 구성이 되어 있는지를 챕터 7에서 간단하게 살펴보도록 할 겁니다. 그래서 그런 장치들의 어떤 기본적인 원리, 작동 원리랄지, 어떻게 작동하는 기능이랄지, 어떤 조건이 필요한지, 어떤 requirement라고 하죠. 그러니까 어떤 특성을 가져야지만 우리가 어떤 것을 측정할 수 있는지, 뭐 이런 것들을 간단하게 챕터 7에서 살펴보도록 하겠습니다. Okay, so as just mentioned, in chapter 7, we'll consider the optical instruments, their function, requirements, and their behavior. Okay? Alright, so basically, optical instruments, in every optical instrument, either UVB spectroscopy, IR spectroscopy, NMR spectroscopy whatsoever, they have 6 major components. Okay? So, and I mentioned that there are 6 major measurements that we investigate for optical spectroscopy, including absorption, fluorescence, phosphorescence, scattering, emission, and chemiluminescence. Okay? So, let's consider the 6 major components of optical instrument. The first one is general design. So they have their general design. The second one is source or energy source and sample holders. They need energy sources and sample holder. They also need wavelength separator. Okay. We learned in chapter 6 that there are various wavelengths depending on the type of light, right? IR, or UVVs, X-ray, gamma ray, etc. But if we need specific wavelength, we need wavelength separator. Okay. There are also slits. We'll come back to this point in detail. Then we need detector. We need to detect light, right? Also, we need signal process and readout. Basically, displays on a screen. We need to read the resulting data. Okay? So, let's check the details. So here shows three different components of optical spectroscopy for different optical measurement. Okay, the first one, A, is for absorption spectroscopy, and B is for fluorescence and phosphorescence, and C is for emission or chemiluminescence. Okay, major difference between A and B and C are, for A and B we need external sources, external energy sources to detect absorption or fluorescence or phosphorescence. But for C, emission or chemiluminescence, we don't really need external energy source such as this or this. In this case, sample itself is the emitter. Sample itself emits light, so we don't need external energy sources. That's the main difference between C and the other two. Okay, let's check each process. So at first, for absorption, we need external energy source. Okay, and we have wavelength selector and sample. So wavelength selector can be located between source and sample, or sample can be located between source and wavelength selector, either way. So let's consider this case. We have external source with wide range of wavelengths, and we select a specific wavelength. It could be either one wavelength or a range of wavelengths. Okay? And that light is emitted to a sample, and then sample absorbs specific wavelength of light. Okay? Then the resulting emission is detected at the detector, and we can read the final result from signal processor and readout. Okay? That's a very basic process for absorption. Okay. How about fluorescence or phosphorescence? Similarly, we have external energy source. Okay, and also wavelength selector. Okay, and we irradiate that selected wavelength to the sample. Okay, and the sample emits fluorescence or phosphorescence. Okay, the reason why we measure the emission at the 90-degree angle is that we need to avoid scattering. We need to avoid scattering from the sample. Okay, we only need to measure fluorescence or phosphorescence. That's why we need to detect the signal, the emission, basically fluorescence or phosphorescence at 90-degree angle. Okay, so from these emitted fluorescence and phosphorescence, sometimes we need to select specific wavelength, and we just detect and read the result. Okay, pretty much similar, right? How about third case, emission or chemiluminescence? As I mentioned, in this case, sample itself is the emitter, right? So we usually use some kind of flame here, right? There's flame or plasma, such as basically thermal energy to excite the sample. And the sample itself emits light, right? Emission or chemiluminescence light. And sometimes we need to select a specific wavelength and detect. Okay? Very simple, right? If you consider the optical characteristics of components, especially for sources and detectors, as you can see, there are various types of sources and detectors. For sources, there are continuum sources and there are line sources. Okay? Continuum sources are basically sources which gives us a range of wavelength of light, such as various kinds of lamp, xenon lamp, argon lamp, hydrogen lamp, etc. Okay. Line sources. Okay. Line sources basically gives us a specific wavelength of light. Not just one line, maybe there could be several wavelengths of light. Okay. So representative examples of line sources are hollow cathode lamp and lasers. Okay. So details will be followed. For detectors, also there are various kinds of detectors. And major two types are photon detectors, basically detect photon, the light, or thermal detectors, basically detect heat or IR radiation. Okay, so there are various kinds. Okay, so we'll deal with these sources and detectors in detail in the following sections. Okay. All right. So as I mentioned, especially for sources, there are major two different kinds: continuum source and line sources. So continuum sources emit radiation that changes in intensity slowly as a function of wavelength. Okay, so basically it gives us a wide range of light. Okay. So continuum sources are commonly used in absorption of fluorescence spectra. So we use these kind of various kinds of lamp: deuterium, xenon, argon, or tungsten lamp. Okay. On the other hand, line sources emit a limited number of lines, limited wavelength, specific wavelength, or bands of radiation. So this is more specific, right, compared to continuum source. So main application is in atomic absorption, atomic or molecular fluorescence, or Raman. And representative examples are hollow cathode lamp of mercury or sodium, or laser. Okay. So let's consider the details, especially for laser. So laser is very important kind of line source, which is commonly used in many applications. As you see, also this is laser pointer, right? Laser pointer. So this is laser, basically. That is that common, right? So laser is abbreviation of light amplification by stimulated emission of radiation. LASER. That's why we call it laser. So basically, laser gives light which is amplified, which is very strong, by some process which is called stimulated emission. Okay? That's why we call it light amplification by stimulated emission of radiation. Okay? Since in laser light is amplified, which emits very intense, very strong light. Also, it gives monochromatic, basically one wavelength. So if you look at this laser pointer, it gives green light, right? One specific wavelength. Some laser pointer gives red light, something like that, right? So it gives us very intense and high power, high intensity light, which is monochromatic. One light, one color, or one wavelength. Okay? In laser, all waves, all lights are in phase. They are the same phase angle. So remember from chapter 6, right? All waves are all in phase and polarized in one plane. It used to be very expensive in the past, but now it's not that expensive. Okay? Advantages of lasers. Some characteristics of lasers include low beam divergence. It gives us very small dot, right? As you see in this laser pointer, right? Very small. monochromatic, single wavelength, coherent, because they are all in phase. So let's see why this is the case for laser. So let's check the details. Let's check the operating mechanism of laser. So here, this figure shows the laser setup. Here we have power supply. Okay. By this power supply, it gives some radiation, which is called pumping source. Okay. And there is active lasing medium, some material which gives laser light. And there are mirror, here mirror and here also mirror. This is totally reflecting mirror, but here this mirror is partially transmitting mirror. Okay, and which by this mirror we get some laser beam. Okay, it's not very clear, right? Up here. So let's move on to the mechanism first. Okay. So you saw pumping, right? In previous slide, pumping here. What is pumping exactly? So for pumping, we need some power supply, some external source. So pumping is the process which is basically excitation of a molecule by other sources, other external sources, such as electrical, radiant, or chemical energy. Okay? So basically, by adding some other external energy sources, we excite molecules. We do excitation, and those molecules would experience vibrational relaxation, and it will be something like this in this energy state, a kind of metastable excited states. So this process is pumping. So basically, it occurs here. By using some external energy source, we excite the molecules. Okay. Then those excited molecules would relax to ground state, right? By spontaneous emission. Okay? And this spontaneous emission or fluorescence is basically incoherent radiation. Okay? So it differs in direction and phases. So these kind of lights are just in different phases and different direction. So that's just normal spontaneous emission. Okay? Normal spontaneous emission occurs inside of this lasing media. Okay? There's another process which is called stimulated emission. As you remember, laser is abbreviation of light amplification by stimulated emission of radiation, right? So what is exactly stimulated emission? So here, during spontaneous emission, we have emitted light here, over here, limited light basically, in various direction and phase, right? Let's say that we have this state, metastable excited states. So molecules are here, basically in excited states. And these excited states are struck, hit by photons produced by spontaneous emission. Okay. So it was here, sitting here, just waiting to be relaxed to ground state, and it has been struck by spontaneous emission in previous process. Then what it happens is these excited molecules relax immediately and simultaneously by emitting photons. So it kind of just like stimulate, agitate, because it is just ready to be relaxed to ground state. And somebody just hit it, and oh, they just fall down to ground state. And since spontaneous emission have a certain direction and phase, it just gives us same. It basically generates same light of emission, which is in same phase and direction. Okay, and that process is repeatedly performed inside of lasing medium. Okay, so inside of this lasing medium, by spontaneous emission, it induces stimulated emission, and stimulated emission also stimulates another metastable excited state, and it repeats inside of this by this meter. So emission, stimulated emission goes this way, but by this meter it goes back. All the non-parallel radiation just go out of this lasing medium, but only radiation in this direction, parallel to these meters, go this way, reflect, stimulate another excited state, repeatedly, many times. And since this partially transmitting meter is only partially transmit, some portion is reflected, but some portion is transmitted to this direction. That's laser beam that we see in this laser pointer. Okay, very simple, right? Actually, there is another process which occur in this lasing media, which is absorption. So there is radiation, either spontaneous or stimulated. If a molecule is in ground state, if it is struck by this radiation, then it could absorb that light and go to the excited state, right? So basically this absorption process is in competition with this stimulated emission. Okay? Alright. It's not that difficult or complicated process. So basically stimulated emission is the main core knowledge of this mechanism of laser. So stimulated emission, a photon incident on an excited state species cause emission of a second photon of the same frequency, basically same frequency, same phase, same direction, which travels in exactly the same direction with the same phase. Okay, so excited molecules, when they relax it to ground state, they produce another light, basically, right, by stimulated emission. So light has been intensified, right? Light amplified, light amplification, laser, right? So this process is repeatedly performed, and it increases intensity of this light. But the problem of this mechanism of laser is that population inversion is necessary for amplification. Population inversion means that, so I mentioned, so let's use the whiteboard. Okay. Alright. Okay. So in laser, So basically, stimulated emission, and absorption are in competition, right? And to amplify light, to make the laser work, we need more stimulated emission, right? And to make more stimulated emission, which means that we need more excited states. So there are excited states and there are ground state. So if there are more excited state molecules compared to ground state, then we can generate stimulated emission line, right? So basically, population of excited state should be larger than the population of ground state, which is called population inversion. Because in normal cases, in normal environment, ground state molecules are much more, right? But to make more stimulated emission, we need more excited states molecule. So we need to make population inversion. Okay? Let's go back. Sorry. Oops. Alright. So we need population inversion to make laser work. How can you do it? So there are two different ways to make population inversion. So the first way is when there are three energy levels: ground state, excited state, and another state. And the second case is 4 level. There are 4 different energy levels. Okay? So in conventional, more like primitive type of laser use 3 level mechanism, but now is more common to use 4 level to make population inversion, because it is much more easier to make this population inversion in 4 level system. So let's see how you do it. So let's say that we have ground state E0, excited state En, and another state EY. And this transition from En to EY is basically non-radiative transition. So from E0 to En is excitation, and there is relaxation to EY, which does not give radiation. And from relaxation from EY to E0, we basically get emission, right? Okay. So in this case, to make this material as laser, we need population inversion in EY compared to E0, right? That's how we get more stimulated emission compared to absorption, right? To do that, we need to pump, we need to excite more and more molecules. Then a lot of molecules here will be relaxed to EY. Then we can get more molecules in this state EY compared to E0, right? So in 3-level system, we need to pump at least 50%, more than 50% of the molecules to excited states. Then we can get population inversion, which would be relatively difficult, right? We need to pump, we need to use a lot of external energy to excite these molecules. On the other hand, in 4-level system, which is much more simpler. So we have ground state E0, excited state En, and another 2 energy level EY and EX. And relaxation between En and Ey from here to here is non-radiative and relatively fast transition. Also, relaxation from Ex to E0 is also very fast and non-radiative transition. Okay? So, this transition from Ey to Ex is the radiative transition that we need to make laser. Okay? So, to make this process as a lasing process, we need population inversion. We need more population in this energy level Ey compared to Ex. Okay? Okay? So, let's say that we excite molecules from E0 to En by pumping. Excited, relaxed relatively quickly to Ey, slowly relax to Ex by emitting light, and quickly relaxes to E0. So basically population of Ex is very small, close to zero, because this process is very fast. Okay? So as long as population of Ey is positive, larger than zero, it is relatively much easier than this case, much easier to make the population of Ey larger than Ex. Okay? So in this four-level system, we can easily make lasing process or population inversion. Okay? So this optical resonance is already explained. Right? So here shows the schematic diagram of light amplification in lasing medium. Okay, so as I mentioned, by pumping, we first excite molecules, and excited molecules strike another molecule, which is in metastable excited state. They are relaxed to ground state by emitting light, and that process is repeatedly performed. Okay, and all processes are performed, right, with same direction, and same phase, right? Okay, so resulting amplified light is go out in this direction to the direction with partially transmitted meter, right? Okay. All right. So we basically saw the lasing mechanism. So there are many different types of lasers: solid state laser, gas laser, dye laser, semiconductor diode laser, etc. Okay. So depending on the type of lasers, they use different type of lasing medium, different molecules. Okay. For example, in solid state laser, we use ruby laser or ND-ARC laser. So ruby laser use three-level population inversion mechanism. So it's just really primitive type, conventional type. But ND-ARC laser uses four-level population inversion mechanism, and which gives 1064 nanometer monochromatic light. Okay. There are also gas lasers which use different types of gases, and dye laser uses some dye which can give different wavelengths of light. Also semiconductor diode laser such as LED. Okay. Second type of optical instrument was sample holder. So there are several characteristics which requirements for sample holders, such as it must contain sample without chemical interaction. It should be transparent to the wavelengths of light. It should be readily cleaned and specific whatever. Okay. So some examples include quartz, glass, or sodium chloride or potassium bromide. Okay, especially for IR range. We'll come back to this point when we deal with IR spectroscopy. Okay, so I believe that you guys already have done UV spectroscopy, right? So we usually use quartz or glass in UV spectroscopy, which is quartz is more expensive, but glass is relatively cheap one. Okay. Okay. All right. So we can just read this part. All right. So here shows the some wavelengths which can be used for several different types of sample holders. Okay, this is the first part of chapter 7.